In the previous lecture, we found out the expression of electric potential due to a dipole. So the potential, it came out to be equal to 1 by 4 pi epsilon naught vector p dot product with r cap. Now what was vector p? It is the dipole moment dot product with r cap. Now r cap is the direction of the position vector of the observation point. So let's say this is the observation point and this is the center of the dipole, and this is also the origin of the coordinate system. So OP vector will be equal to R vector. So that is the position vector of the observation point, and R cap is the direction in which this OP vector is pointing, and this angle was assumed to be equal to theta. So this angle is the angle between OP vector and the dipole moment, because dipole moment points from negative charge towards the positive charge. So this can be written as vector p dot product with r cap. It can be written as p cos theta, because theta is the angle between r cap and p vector. So this can be written as 1 by 4 pi epsilon naught p cos theta divided by r squared. So, and in the previous lecture we also saw that electric field, it comes out to be equal to negative of the gradient of the electric potential. So electric field intensity is always equal to negative of the gradient of electric potential. Now for the case of dipole moment, we know what is electric potential. So we have just derived the formula of electric potential. So using this formula, we will now derive what is the electric field for the case of an electric dipole. So using this formula as well as using this expression of potential, we will find what is the electric field intensity due to a dipole. So now we are going to obtain the expression for electric field. So this was the dipole which we have considered. So this is minus q charge and plus q charge, and these two charges, they were separated by a distance of 2L. And P was the observation point at a distance of r from the center of the dipole, and theta was the angle between OP vector and this direction, which is the direction of the dipole moment. Now let's say this is the observation point. So this we have supposed to be the point where we want to find the electric field. And at this point we know the expression of potential, that is given by p cos theta divided by 4 pi epsilon naught r square. As you will change this observation point, this r will change as well as this theta will change. So on changing this observation point, this theta and r both will change. So therefore potential will change as you will change the observation point. So let's consider this observation point. It has three coordinates. So let's say the x coordinate is given by x, then y and z. And let's consider this axis, this whole axis. This is the positive x-axis, and from this origin of the coordinate system, let's say this is the negative x-axis. So this is the center of the dipole as well as it is the origin of the coordinate system, and this point P, it is placed at x, y, z. So let's first of all, we will make the projection of this OP length on the x-axis. First of all, we will draw the projection of this OP on the x-axis. That is, we will draw a normal on the x-axis. So now we have drawn a normal from P point on the x-axis. So what will be this length from the center of the coordinate system? So this is the center of the coordinate system. Now this is the y-axis. This is the plus x-axis. So what will be this particular length? So this particular length will be equal to x. So this length, which is the projection of OP on the x-axis, this will be equal to x, because this is the observation point with coordinates x, y, z. So this point has a projection of x on the x-axis, and it will have a projection of y on the y-axis and z on the z-axis. But here we are just considering the projection on the x-axis, so this length will be just equal to x. Now in this right angle triangle, this particular right angle triangle, here we have theta and we have x and we have this length as r. So what will be cos theta in this case? Because in the expression of potential we have p cos theta, so we need cos theta. So what will be cos theta in this triangle? Now cos of any angle is equal to base upon hypotenuse. So what is base? Base is equal to this length, which is nothing but equal to x. So this is equal to x, base divided by hypotenuse. So what is hypotenuse? It is equal to OP length, and that is equal to r. So this is the expression that we will use for cos of theta. As well as in this expression of potential we have r square. Now r is the distance of this point from the origin of the coordinate system. So this point is given by x, y, z. Now what will be r square? So r square from this case will be equal to x square plus y square plus z square. So using the geometry, we can find r square will be equal to x square plus y square plus z square. So we need r square from this expression. Now we want to find the electric field at this point. So to find electric field, we will use this formula, that is, we will find the gradient of the electric potential. Now what is this gradient? So this del operator, it has a form. So del operator is given by I cap del by del x plus j cap del by del y plus k cap del by del z. So this is how we define the del operator. Now del operator, it is operated on the scalar function, which is electric potential in this case. So this electric field intensity, it will come out to be equal to negative of, so negative sign it will remain as it is. Then we have the gradient. So gradient will be, so del operator will be I cap del by del x plus j cap del by del y plus k cap del by del z, and this will be operated on the electric potential. And what is electric potential? It is p cos theta by 4 pi epsilon naught r square. Now p divided by 4 pi epsilon naught, so p divided by 4 pi epsilon naught, it is a constant, because electric dipole, the dipole moment will be constant, and this 1 by 4 pi epsilon naught, it is also a constant. So p by 4 pi epsilon naught, it can be taken common. So p by 4 pi epsilon naught, and we have cos theta. Now what is cos theta? This we have already seen. Cos theta is equal to x divided by r. So cos theta, this cos theta will be equal to x divided by r. So in the denominator we will get r cube. So in actual what we need is, we need r cube. So we have r square. So from here r will be equal to square root of, that is x square plus y square plus z square whole power 1 by 2. So this will be the expression of r, but we need r cube in this case. So r cube will be equal to x square plus y square plus z square power 3 by 2. So we have done cube on both hand sides. So cos theta is, we will substitute cos theta as x divided by r, and what will be r cube? R cube will be equal to this expression. So we will just insert this formula over here. So p by 4 pi epsilon naught cos theta divided by r square. So that will be equal to minus of this whole expression over here. So this whole del operator will come over here, and then we will have p by 4 pi epsilon naught, that is a constant, so it can be taken outside the operator. So p by 4 pi epsilon naught, it can be taken outside. With a negative sign, it will remain as it is. Then here we will have on the right hand side, we will have x divided by r cube. So cos theta is x divided by r. So we will be left with x divided by r cube. So x will remain as it is. Divide by r cube is nothing but x square plus y square plus z square power 3 by 2. And this whole del operator, it will be written as it is. That is I cap del by del x plus j cap del by del y plus k cap del by del z. Now we will evaluate this operator. That is, now we will operate this del operator on this scalar function. So we will get three components. So in the del operator we have three components, that is del by del x, del by del y and del by z, del z. So now we will operate each and every operator individually. First of all, we will operate del by del x on this scalar function and I cap will remain as it is. Then we will operate del by del y on the same scalar function and j cap will remain as it is. Similarly, we will operate del by del z on this scalar function and k cap will remain as it is. So what we will get, minus p by 4 pi epsilon naught, it will remain as it is. Then we will first of all we will operate this first term on this scalar function, that is I cap del by del x, it will remain as it is. It will operate on this scalar function which is x divided by x square plus y square plus z square power 3 by 2. Then we will operate this second operator, that is plus j cap del by del y, it will operate on the same scalar function which is x divided by x square plus y square plus z square power 3 by 2. And then we will operate this last operator, that is k cap del by del z, it will operate on x divided by x square plus y square plus z square power 3 by 2. So now we will just solve these terms. So first of all we will solve this del by del x operating on this function. So we will solve this. First of all we will solve this operator, then we will solve this term, and at last we will solve this term. So on solving all these terms, on solving all these derivatives, partial derivatives, we will insert the results into these expressions and then we will get the final result of the electric field intensity at this point P. So now the task is to find these partial derivatives individually. So I will solve the first operator, that is del by del x, x by x square plus y square plus z square power 3 by 2. So first of all I will solve this partial derivative, and these other two partial derivatives, they can be solved in a similar manner. So they can be solved in a similar manner by you. So first of all we will solve this derivative with respect to x, and keep in mind this is the partial derivative, and whenever you are doing the partial derivative with respect to a variable, only that particular quantity is a variable. All other quantities over here, let's say that is y and z, all other terms, they will be treated as constants. So here we are doing the partial derivative with respect to x, so only x will be treated as variable, and all other, for example y and z, so these will be treated as constants. So first of all we will write it in a manner that del by del x, and x will remain as it is, and this term in the denominator we will take it into the numerator, so that will be x square plus y square plus z square. Now power will become negative, so that will be minus 3 by 2. So we have just simply taken the denominator in the numerator. So now over here we have this function which is a function of x, and we have this function which is a function of x. So we have to do the derivative. We have to use the formula of derivative of two functions which are multiplied. So the derivative of two functions which are multiplied, it is equal to, first of all, first function will remain as it is, that is x will remain as it is. Then you have to do the derivative of the second. So we will do the derivative of second, so which is x square plus y square plus z square power minus 3 by 2. Then second function will remain as it is, plus second function it will remain as it is, that is x square plus y square plus z square power minus 3 by 2 into derivative of first function. So derivative of partial derivative of x with respect to x, that is nothing but equal to 1. So multiplied by 1. So now we have to solve this term. So x into derivative of this function with respect to x. So first of all we will take this power. So derivative of x power n is equal to n into x power n minus 1. So that we already know that derivative of x power n, derivative of x power n is equal to n into x power n minus 1. So we will use this formula over here. So we have power minus 3 by 2. So minus 3 by 2 it will come in the front. So minus 3 by 2 into x square plus y square plus z square power minus 3 by 2 minus 1, that will be minus 5 by 2 into derivative of the function which is inside the bracket. So we are doing derivative with respect to x, so we have to do derivative always with respect to x. So here we will have another term which will be into derivative of the function which is inside the bracket. So that is x square plus y square plus z square. So we have to do its derivative with respect to x. So that will be nothing but equal to 2x, because y square and z square, they will be treated as constants. So their derivative with respect to x will be equal to 0. So only we have to do the derivative of x square with respect to x. So that is nothing but into 2x and plus this term, it will remain as it is. So here we have just solved the first term, and second term it will remain as it is, which is x square plus y square plus z square power minus 3 by 2. Over here we will also substitute this expression, that is r cube is equal to x square plus y square plus z square power 3 by 2, or you can say r is equal to this expression. Over here in this particular expression we have x square plus y square plus z square power minus 5 by 2. So this term, this particular term, it can be written in the form of r also. So r is equal to x square plus y square plus z square power 1 by 2, but here we have minus 5 by 2. The power is minus 5 by 2. So this can be written as x will remain as it is, minus 3 by 2 remains as it is. So this term, it will be written as r power minus 5. So you will do the power minus 5 on both hand sides and you will get this expression into 2x. It will remain as it is, plus here we have x square plus y square plus z square power minus 3 by 2. So you will do power minus 3 on both hand sides. So you will get this expression equal to plus r power minus 3. So this is the expression that you will get for the case of partial derivative with respect to x. So this is the first term that we have solved. So we have solved this term. Now when you will solve the other two terms, that is the partial derivative with respect to y and partial derivative with respect to z. So this term, it will come out to be equal to it will come out to be equal to minus 3xy divided by r power 5, and this last term, it will come out to be equal to minus 3xz divided by r power 5. So you can solve these two terms by yourself and you will get these expressions. So this is the expression for the first term, then this is the expression for the second, and this one is for the third. And you have to write this I cap, j cap and k cap along with these terms. So that will give us the total electric field at that particular point. So on substituting all the expressions, you will get electric field intensity at a point due to the electric dipole. It will come out to be equal to these expressions. So here I have just substituted all the results of derivative that we got in the previous page. So you will get this expression. Now we will just simplify this expression more. So we see that here we have r power 5, r cube and r power 5 and r power 5. So let's say first of all we take r power 3 common from the denominator. So we will take r power 3 common from all the denominators. So you will get minus p by 4 pi epsilon naught 1 divided by r cube. So I am taking r cube common from the denominator. So you will get I cap. And here I have taken r cube common. So here I will be just left with 1. And 1 this 1 I will write in the front. So I will get 1 minus 3x square divided by. So r cube will be taken common. So I will be just left with r square. Then minus j cap 3xy divided by r cube is taken common, so we are left with r square. Similarly, minus k cap 3xz divided by r square will be left inside the bracket. So this is the expression of electric field intensity at a point due to an electric dipole. But now we are going to find the magnitude of the electric field. Now this electric field, it is in its vector form. Here we have I cap, j cap, k cap. So this is the vector form. But now we are interested to find the magnitude of this electric field. So to find the magnitude of electric field, so if I have a vector, A vector, which is given by ax I cap plus ay j cap plus az k cap. So I am given with its x component, y component and z component, and if I want to find the magnitude of this A vector, so magnitude of A vector is given by under root of ax square plus ay square plus az square. So this is how we find the magnitude of any vector. So the similar formula will be used over here. Here I have the x component, y component and z component. So simply I will use this formula to find the magnitude of the electric field intensity. So these are the x, y and z components of the electric field. So I have divided this equation into x component, y component and z component of the electric field. So I have written all the components separately. So now I am finding the magnitude of the electric field using this formula. So electric field's magnitude will be equal to under root of Ex square plus Ey square plus Ez square. So from here I will find magnitude of electric field, that will be given by under root of x square, under root of Ex square plus Ey square plus Ez square. So in this whole in these all terms we have p by 4 pi epsilon naught r cube common. So we are doing the square of all the terms. So we will also do the square of p by 4 pi epsilon naught r cube in every term. So that is common in every term. So we are doing the square of all these three components. So this p by 4 pi epsilon naught r cube, it will be common. So we can take it outside the under root. So we will have p by 4 pi epsilon naught r cube, it will remain outside the under root, and inside the under root you will have just 1 minus 3x square by r square whole square, then you have plus 3xy by r square whole square, then you have 3xz by r square whole square. So I have just skipped the one step in between, that is we are doing the square. So we will find Ex square, we will find Ey square and we will find Ez square, and then we will add all these terms, all these squares of the x, y and z components, and then we will do the under root. And if after doing the under root, this p by 4 pi epsilon naught r cube whole square, that can be taken outside the under root, so it will just become p by 4 pi epsilon naught r cube. So I have missed one step over here, but you have to write each and every steps. That is, first of all you will find Ex square, Ey square, Ez square, and then you will do their summation, and then you will take the under root. So you will get this final result. So now we are going to solve these terms which are inside the square root. So I will open the first term. Here I have a minus b whole square. So I will get p by 4 pi epsilon naught r cube. It will remain as it is, and inside the under root I will get a square, which is 1. Then we have b square, which is plus 9x power 4 by r power 4. Then I have minus 2ab, which will be 6x square by r square. So just I have used the formula of a minus b whole square. Then I am doing the square of these terms, which will become 9x square y square by r power 4. and the last term I will get 9x square z square divided by r power 4. Now let's club this term and this term, that is the terms whose denominator is r power 4. So now we are going to club these three terms. So what we will get p by 4 pi epsilon naught r cube, and inside the square root, first of all 1, then minus 6x square divided by r square, they will remain as it is, and we are clubbing these two terms. Now in these three terms, what we have in common? We have 9 common, then we have r power 4 common, as well as we have x square common. Here also we have x square, here we have x square, and here we have x power 4. So x square is also common. So what are the common quantities? We have 9x square divided by r square, and inside the bracket we will be left with x square. So from the first term we will have x square, from the second term we will be just left with y square, and from the last term we will have z square. Now what is this x square plus y square plus z square? So on the previous page we have written that r square is equal to x square plus y square plus z square. So we can replace this term by r square. So that r square, so this will be equal to r square. So this r square, it will cancel with the r square in the denominator. So we will be just left with 9x square. Here we will have r power 4 as common. So we are taking r power 4 common. So inside the bracket we will have x square plus y square plus z square, and this will be equal to r square. So this r square will cancel with r square in the denominator. So we will be having x square, 9x square divided by r square. So we will get magnitude of electric field as equal to p by 4 pi epsilon naught r cube, it remains as it is, and inside the square root we will get 1 minus 6x square by r square. So these two terms will remain as it is, and this term will become plus 9x square divided by r square. Now here we have 9x square, and here we have minus 6x square divided by r square. So that will be equal to p by 4 pi epsilon naught r cube under root of 1 plus 3x square divided by r square. So we will be left with this term. Now this x by r we have already written as that cos of theta is equal to x by r, whereas here we have x square by r square. So x square by r square will be equal to cos square theta. So magnitude of the electric field will be equal to p by 4 pi epsilon naught r cube under root of 1 plus 3 cos square theta. So this is the final result of the magnitude of electric field intensity due to an electric dipole. So here will be r cube. So the terms p by 4 pi epsilon naught r cube, it will remain as it is, and this will become under root of 1 plus 3 cos square theta. So this is the final result of the magnitude of electric field intensity due to an electric dipole. Now we are going to start with the article of electric potential due to a quadrupole. So earlier we did the electric potential due to an electric dipole. So in the case of dipole we have two equal and opposite charges, whereas in the case of quadrupole we will have 4 charges. So in total we will have 4 charges, and summation of the charges, all the charges will be equal to 0. So as in the case of dipole, the summation of all the charges is equal to 0 because we have equal and opposite charges. And in the case of quadrupole also, we will have 4 number of charges, and the summation of the charges will be equal to 0. So first of all, in the starting of the chapter, we had a point source charge. If we have a single charge, then that single charge is also called as monopole. So the another name of a single point charge which is placed in space, it is called as monopole. And if we have two equal and opposite charges, let's say this is plus q and this is minus q, which are separated by a certain distance. So these two charges, they are equal and opposite and they are separated by a particular distance. So this system is also called as dipole. So this we have already seen in the previous lecture. And if we have four number of charges, now here we have minus q charge, here we have minus q charge, but at the center, that is in between these two negative charges, I have 2 plus q charges which are superimposing on each other. So this total will become plus 2q. So these two charges, they are superimposing on each other, so that will become plus 2q, and minus q charges on the left hand side and 1 minus q charges on the right hand side. Similarly, you can also draw another quadrupole in which you will have plus q over here and you have plus q over here, but you will have minus 2q at the center. So this system, it is called as quadrupole. And more precisely, it is called as linear quadrupole because the charges, they are placed in a line. Now the another form of quadrupole is this structure where we have equal and opposite charges which are on the opposite corners. So here I have minus q charge, here I have minus q charge on the opposite corners, and here I have plus q charge and here I have plus q charge. So this system of four charges of equal and opposite charges, it is also called as quadrupole. But this is the two-dimensional quadrupole. So this one is also a quadrupole, but it is a linear quadrupole because charges are placed on a line, whereas this system is the quadrupole, but it is a two-dimensional quadrupole. Now in this article we will find the electric potential due to a quadrupole, but we will just study the linear quadrupole. That is, we will have plus q charge over here and plus q charge on the other side, and at the center I will have minus 2q charge. So this will form a linear quadrupole, and we are interested to find what is the electric potential due to this linear quadrupole at any point P in the space. So this P point is the observation point, and this center will be considered as the origin of the coordinate system. As in the case of electric dipole, we considered this center as the origin. So in this case also, here I have plus q charge, here also I have plus q charge. So this center will be considered as the origin of the coordinate system. So this, let's say we denote it by capital O. Let's consider the distance of this plus q charge from this plus q charge. Let's say this total distance is equal to 2L. As in the case of electric dipole, we consider the distance between these two charges was equal to twice of L. So in this case also the distance between these two charges is considered to be 2L, and this is considered to be as the center of the coordinate system, that is the origin of the coordinate system. So this length will be considered as the position vector of this observation point. So in this case also, let's say I denote this side as L and this point as N, and this point, it can be considered as O because it is the origin of the coordinate system. So this length OP vector, so let's say this is the R vector. As in the case of electric dipole also, we considered OP vector as R vector. And this ON vector, this will be the position vector of this plus q charge, and that will be equal to L vector because this is the half length. The total length is equal to 2L, so this half length will be equal to L, and this vector is represented by L vector. And in a similar manner, this OL vector, this vector will be minus of L vector because it is in the opposite direction to that of ON. So this is how we will denote all the position vectors. Now to find electric potential at this point, first of all we will find electric potential due to plus q, this charge, then we will find electric potential due to plus q this one charge, and then we will find electric potential due to this minus 2q charge. So then we will just do the summation of all the potentials, and then as a result you will get the total electric potential at P point due to this whole linear quadrupole. So to find the electric potential, we need to know the distance of these charges from the observation point. So what do we need to know? We want to know the distance of this observation point from these individual charges. That is, we must know what is LP, then we must know what is OP. So this OP is also already supposed to be R. So this OP is known to us. What we need to find is LP in terms of R and L. So R and L are known to us. So we need to find LP in terms of R and L, and similarly we need to find NP in terms of L and R. So we will simply use the triangle law of vector addition. So first of all, the potential at P point, it will be equal to 1 by 4 pi epsilon naught. Then if you have plus q, if you are considering this source charge first, so 1 by 4 pi epsilon naught plus q divided by the length, that is the distance of the observation point from the source charge, so that is LP. Then I have this minus 2q charge. So the potential at this observation point due to this minus 2q charge, it will be equal to 1 by 4 pi epsilon naught minus 2q divided by the distance. So I have minus 2q divided by distance, that is nothing but equal to R, or I can just write OP. Then I have the last point source which is left, which is plus q. So the potential at P point due to this plus q will be equal to plus q divided by NP, and 1 by 4 pi epsilon naught, it is common to all these terms. So now we are interested to find what is 1 by LP and what is 1 by NP in terms of the known variables. So what are known variables? R is known to us and this L is known to us. So using the triangle of vector addition, we will find 1 by LP and 1 by NP as we had found in the previous case of electric dipole. So from there we found 1 by NP. 1 by NP, it came out to be equal to 1 by R square plus L square minus 2RL cos of theta power 1 by 2. So using this triangle using this triangle on the right hand side, we will find the NP in terms of L and R, and then we will do the dot product of that equation with itself. From that we will get NP square. So the whole procedure will remain the same. So you can revise, you can go to the previous article of electric dipole, how we found 1 by NP and how we found 1 by LP. So in this case the formula will remain the same. 1 by NP, it will come out to be equal to this form. So now we are going to take R square common from the denominator. So R square will be taken common, and let's say first of all we take this whole thing in the numerator. So when you will take this whole thing in the numerator, you will get R square plus L square minus 2RL cos theta power minus 1 by 2. And you will take this R square common. So on taking R square common, you will get R square power minus 1 by 2 outside the bracket. So that will become 1 by R. So R square will be taken common from all these terms. So that R square power minus 1 by 2, that will be 1 by R. So that will be outside the bracket, and inside the bracket we will have 1 because we are taking R square common. So first term will become 1, second will become L square by R square, and third term will become 2L cos theta divided by R. So you will get divide R by R square, and R will cancel with 1 R in the denominator. So you will be just left with 1 by R in the third term, and power minus 1 by 2. And similarly, you will get the expression of 1 by LP. So using this triangle on the left hand side, you will get the expression of 1 by LP, and that will be similar to this form, but there will be a difference of sign. So here will be plus sign for the case of 1 by LP. So that will be equal to 1 by R, 1 plus L square by R square plus 2L cos theta divided by R power minus 1 by 2. So this is the expression of 1 by NP and 1 by LP. So in the next lecture we will use the approximation, and then we will use the binomial expansion, and we will simplify this expression. So we will neglect the higher order terms using the binomial expansion, and then we will insert the final form of 1 by NP and 1 by LP in this formula, and we will get the result of the electric potential due to a linear quadrupole. So that we will continue in the next lecture.